Today we're going to still continue graphing rational functions, but we're going to focus on the slant asymptote. So this is the same sheet that we saw for last lesson. Scrolling down to slant asymptote, if the degree of the numerator is 1 more than the degree of the denominator, so we would have to have something like x cubed over x squared, but x to the fourth over x squared would not give us a slant asymptote. To find the slant asymptote, you divide the numerator by the denominator and ignore the remainder. And that gives you an equation of a line, y equals mx plus b. That will be your slant asymptote. So our essential question is, how do we graph a rational function with a slant asymptote? The first thing we're going to do is practice finding that slant asymptote. Notice in example 1, the degree of the numerator is 2. The degree of the denominator is 1. So the numerator has a degree that is 1 more than the degree of the denominator. So we will divide. We have x squared plus 0x, don't forget that placeholder, plus 5, divided by x. X times x gives us x squared. Subtracting, bringing down that 0x. X times 0 is 0x. Multiplying, subtracting, bringing down that 5, which is our remainder. We ignore the remainder, and of course x plus 0 is really just y equals x. That's the equation of our slant asymptote. We're not going to graph this whole function, we're just going to graph the slant asymptote. The y-intercept is 0, and the slope is 1. So rise 1, run 1. I like to use the whole graph because I have a hard time drawing straight lines. And for my asymptotes, I like to keep them dotted. So I'm just going to throw arrows on the end and call that my slant asymptote. Another one, just practicing graphing that slant asymptote. The degree in the numerator is 3. The degree in the denominator is 2, which is 1 more than. So we set up our long division. We have a 0x squared and a 0x. So don't lose those placeholders, divided by x squared minus x. X squared times x gives us x cubed, multiplying that x by both terms. Distribute that division, and then you can add your like terms, bringing down that 0x. X squared times 1 gives us x squared. Multiplying that 1 by both terms, distributing our division, bringing down the minus 1. X squared does not go into x, so that's a remainder, which we ignore. So the equation of our slant asymptote is x plus 1, which means our y-intercept is 1, and again, our slope is 1. Rise 1, run 1. Or you can fall 1 and go to the left 1. And putting that all together and graphing the entire function with a slant asymptote. First of all, we figure out our domain restriction, setting the denominator not equal to 0, adding 1 to both sides. Our domain is x cannot equal 1. In order to determine if that's a vertical asymptote or a whole, we need to factor that numerator, what multiplies to 1 and adds to negative 1. Nothing does that, so our numerator doesn't factor, which means that will be a vertical asymptote at x equals 1. The power in our numerator is 1 more than the power of the denominator, so we have a slant asymptote. For this division, I can use synthetic division. That denominator is a binomial with the highest power of 1. So I'm going to use those coefficients of the numerator, 1, negative 1, and 1. Taking that minus 1 out of the asylum, out of the grouping with x, and making it positive, dropping the 1, multiplying by 1, adding, multiplying, and adding. The equation of our slant asymptote is y equals x, ignoring the remainder. X-intercepts occur when we set the function equal to 0. Really, we just need to worry about where the numerator is 0. If we multiply both sides by the denominator, it goes away. This one we already tried to factor and it doesn't. So we'll have to use quadratic formula to get our zeros. Opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. Looking at what's under the radical, we have 1 minus 4 or negative 3, which means we have imaginary zeros, which means we don't have any zeros that we can graph on this function, so there are no x-intercepts. Y-intercept occurs when you substitute 0 in for x. We have 0 squared minus 0 plus 1 over 0 minus 1, which gives us 1 divided by negative 1, or negative 1. So our y-intercept is 0, negative 1. Does our graph have symmetry? Substituting negative x into the function. In the numerator, the negative will square out. Negative minus the negative is positive. In the denominator, the negative does not cancel. If we try to factor a negative out, you could only factor it out of the numerator or the denominator, not both. As you're looking through, we have some terms that are opposite and some that are not, so this has no symmetry. We didn't get a ton of information about this graph, so we will probably have to do a t-chart. Let's start by graphing those asymptotes. We have a vertical asymptote at x equals 1. We have a slant asymptote at y equals x. So our y-intercept is 0 for that line, and we have a slope of 1. The only point we know is we have a y-intercept at 0, negative 1. To the left of the vertical asymptote, I'm just going to use my two asymptotes and my y-intercept to sketch this graph. I know that it will approach that slant asymptote, and it will approach the vertical asymptote. However, I have no information for what's going on the right-hand side, so I'll substitute a few values in. I'm going to start with 2 and 3 and see if that'll give me enough information with those asymptotes to get this graphed. Subbing 2 into my function, 2 squared minus 2 plus 1 over 2 minus 1. In the numerator, we have 3. In the denominator, we have 1. Subbing in 3. In the numerator, we have 7. In the denominator, we have 2, so 7 halves, or 3.5. Plotting those points, 2, 3, and 3, 3.5. I can see again it's going to approach those two asymptotes.